pre-trap using The title of the talk is Preparation and Thermal Pretreatment to Supported Iron Alloy Catalysts.
Thank you, Mr. Chairman. Ladies and gentlemen, let me first see how I got the device switched on. So there we are.
Good doing.
Try pointing at the screen.
No,
You have to turn the projector screen first.
Somebody turn the projector back there? Okay. This is our.
Yeah, turn it off.
Well, stuff turn it on.
Okay,
you go.
Okay, there, you have it.
There the title of the talk, and I'm going to talk about the preparation and thermal pretreatment, especially of supported iron catalyst. And well, I must say I was working on that subject from the 60s already. And the second point indicates why we are still interested, or at least I'm still interested in iron. Iron provides a rapid dissociation of CO. You get a subsequent molecular absorption of CO in between the dissociated CO, and you get a removal of the adsorbed oxygen, and you get a rather good Fischer-Tropsch activity, though the stability is fairly low. Now, if you want to produce a good Fischer-Tropsch catalyst based on iron, you want to have a high fraction of reduced metal, especially iron. You want to have no formation of elementary carbon, no deposition of carbon, and no formation of stable metal carbide. But especially the high fraction of reduced metal is highly important. When I started out in the 60s, I had the idea to improve the very old ammonia synthesis catalyst. And we were trying to put iron onto silica, and we were having the idea that we could reduce the pressure, even go down to atmospheric pressure. At DSM, after a very intensive reduction treatment, they had an ammonia catalyst that was able to produce ammonia already at room temperature. And when I proposed an experienced chemical engineer to produce ammonia at atmospheric pressure, he let me calculate the diameter of the reactor for having not too high a pressure drop. Well, actually the diameter was of geographical dimensions from one village to another village. So I think atmospheric pressure is not that bad. But reduction of iron, especially supported iron, is a very difficult job. So, first of all, you have to do with the equilibrium. Usually we are accustomed to nickel and copper, which is very easy to reduce, but with iron the thermodynamics are unfavorable, and you have to decrease the amount of water present before you can reduce the iron. Now, to remove water out of porous support systems is rather difficult. If you have nickel on silica and you have just a silicon plate, it's easy to get silicides of nickel if you are just reducing and you are decreasing your water vapor pressure. But within a porous material, it's extremely difficult to decrease your water vapor pressure. And therefore, the reduction of iron is very difficult. It's difficult to remove the water out of the porous system. And moreover, iron too is liable to react with supported silica, alumina, and magnesia. And then it reacts to a non-active component. So that's the problem. Now, my lecture is just going as a patent application. First of all, I have to indicate all the difficulties of the state of the art. And if you want to claim an invention, it must not be a discovery. So then, surprisingly, you get a means that you can go around, well, in patents around all the difficulties, and here around some of the difficulties. So first, the difficulties. You are reducing iron oxide. And you may ask whether the stability of oxygen sitting on an iron surface is not higher than the stability of the thermodynamic stability of iron oxide. And it turns out to be true on most surfaces of iron, except the most stable 110 surface. So if we are oxidizing an iron surface, or just exposing an iron surface to oxygen, and we are raising the temperature, you find the formation of oxides. So the thick layer of oxygen that is established at room temperature at 200 degrees C goes to these iron oxide crystallites, leaving a monolayer of oxygen on the surface. If you are adding hydrogen, and you can do that in an ultra-high vacuum equipment only at low pressure and raising the temperature, you can remove the oxide underneath the surface fairly rapidly. But there remains the oxygen layer at the surface. And the bead pattern of the 100 surface containing oxygen is even more sharp than the bead pattern without oxygen. And only a little bit of that oxygen is sufficient to completely depress the activity for nitrogen adsorption. So we have the idea that the surface becomes more stiff if the oxygen is sitting there, and by means of low electron scattering we could establish that the oxygen is just sitting on the fourfold sides and rather stable. By the way, this can explain why just a little bit of water, far less than is thermodynamically required to suppress the reduction of iron oxide, is sufficient to decrease the activity of an ammonia synthesis chemical. So that you have to care for the reduction to make clean iron surfaces, except the iron on the surface is a difficult job. I indicated over here just some temperature reduction profile, and I only want to draw your attention to the top. We have there unsupported iron oxide, and this is an iron oxide of a surface area of the order of 400 square meter per gram. And usually you find if you have an unsupported metal oxide, it's quite easy to reduce. But here you see a rather easy reduction indeed, but first you have a reduction to magnetite, and subsequently you have a reduction of magnetite to metallic iron. If you reoxidize this material, and that is centered strongly due to the reduction to the metal atoms are rather mobile, you get a big oxide particle, and you can reduce the oxide particle in one step. So this is due again to the effect of transport of water out of the porous system. You cannot remove the water rapidly, and here you have the equilibrium conditions only leading to magnetite. With this system, you can go immediately to such a low water vapor pressure that you can reduce immediately to the metal. If we now are going over to iron applied onto alumina, I first of all must say that just the usual impregnation procedure is not very good for applying iron to alumina. If you want to have dissolved iron, you have to have a pH value below 2. If you are above 2, you have actually precipitated iron, very small iron oxide particles. And a pH of 2 leads to dissolution of your alumina and subsequent reprecipitation. It is rather difficult to predict the results. Also with silica, you get not an attack of silica, but just impregnation and drying leads to clustering of the iron particles. What we are doing is injection of an acid iron 3 nitrate solution into a suspension of the support that's kept at the pH level above about 6, and then you get a very good dispersion. But it's not always the case that a very good dispersion is favorable, because with a good dispersion you have every reason for the iron to react with the alumina to an iron aluminate. And you have the same with silica. A very good dispersion often leads to unexpected results. Well, here is indicated the hydrogen consumption as a function of the temperature, and the temperature was raised by about 5 degrees C per minute. And first of all, we have over here an FeO08 sample. Highly porous, the FeO08 has the surface area of around 407 square meter per gram. And you can see that first we have the reduction to magnetite, and then we have the reduction to metallic iron, and over here 1000 K, so you can see that around 800 K the reduction is complete. If you are going to dehydrate the material, you get the pattern indicated in the second curve, over here, the second plot, and then you can see that it's more difficult to start a reduction. The dehydration brings about a drop in the surface area down to about 50 square meter per gram, and you are removing all the lattice vacancies and all the lattice defects, and then it's more difficult to start a reduction. Over here, and I will indicate you that within a moment, you get dehydration. Dehydration leads to a defect iron oxide, and it's rather easy to reduce the iron oxide. This is the pattern, the third curve. We were measuring on Fe2O3, alpha Fe2O3, that was prepared by the decomposition of iron carbonate. And you can see again the two-step reduction, and it is slightly more active than this material that has been kept at a rather high temperature. Then we have here a graph of an iron aluminate, and you can see, and below we have a graph of an iron aluminate, and you can see it's much more difficult to reduce the iron aluminates. Now you can say, well, it stands to reason, because you have a much more porous material, it's much more difficult to get rid of your water. But here we have the curve, where we have the same FeO8 mixed up with alumina, and we also did a reduction, and you can see that the presence of alumina didn't lead to a more difficult reduction. So there must be an interaction between the iron oxide and the alumina, which renders the iron oxide rather difficult to reduce. Here are combined, and again, here's the hydrogen consumption as a function of the temperature, and we compare the temperature per reduction, so this is the hydrogen consumption, with the evolution of water. So you can see if you are heating up the sample in water, and this is again the FeO8 sample without a support in water, you see first of all the dissolption of some water, and then you get dehydration, and at the moment of dehydration, it's also the reduction that starts, that indicates that you get a defective structure actually. Here we have the same sample, and this is iron FeO8 onto alumina, and if we are calcining it previously onto alumina, you get a reaction that runs earlier at lower temperature, and that's due to the fact that the defects are apparently stabilized in the direction of the alumina. This is the FeO8, it's indicated previously again. Dehydration, this is water, salt water, but dehydration at the same temperature as the start of the reception after calcination, a much less reactive sample. And here we have a thoroughly dried catalyst. This catalyst has been thoroughly dried at low temperature, and you can see that it doesn't make too much difference if you are removing the water. You have not a very big difference. So what we also were doing, I just want to go back to this slide, we were measuring at where the arrows are indicating the X-ray diffraction pattern. And then we find here only the diffraction pattern of alumina. Over here is some magnetite. Here we have magnetite and FeO. And here we have only FeO plus iron, metallic iron. But if you do the measurement, the reduction is over here far from complete. Whereas with the unsupported samples, you have a complete reduction. The reduction with the supported catalyst is far from complete. It's very difficult to reduce the supported catalyst. Now we want to assess the presence of the FeO and the intermediate of FeO. And over here we have 3 samples. This is iron onto alumina. This is a physical mixture. The alpha FeO with alumina, and this is iron on silica. I will not discuss further for time limitation the iron on silica, but you can see that we have very small particles of iron oxide, hydrated iron oxide present over here. If you are cooling down to 77K, you get this busbar pattern, and only at 4.2K, you get the resolved busbar pattern indicated very small particles of Fe2O3 after dehydration. Over here, you can see for the supported catalyst, iron on alumina, the behavior on reduction. Well, the first reduction not about any difference, and the second reduction leads to magnetite together with some iron 2. And if you are raising the reduction temperature, it's interesting that you get a disappearance of the magnetite and no formation of metallic iron, but you get formation of iron 2 oxide. So FeO Weustite is being formed at the expense of the magnetite. And finally, at a fairly high temperature, you have metallic iron together still with iron 2, with FeO. So with the iron on alumina, in spite of the fact that FeO is not thermodynamically stable, it is being stabilized by the alumina, and we have the same phenomenon more or less on silica. If you compare that with the physical mixture of the FeO weights and the alumina, you just see the magnetite, and the magnetite does not disappear, but the magnetite is going over into the metallic iron. Well, we were trying to apply iron onto carbon, because with carbon you don't have so much absorption of water, so you would expect this much more easier. This is with Thierry's procedure, where we have the iron oxide particles onto this finely divided soot carbon. You can apply iron quite well to carbon. Here you see the means of FeO weights, but if you are reducing, you get particles like this. There is no good interaction between the iron, metallic iron, and the carbon. You can see that here better. There are some FeO weights particles, and you see they are reacting to these rather big iron particles, and it's completely different from nickel. If you have here nickel, FeO weights 2 times, and you have there the reaction. You break up, so the nickel contacts quite well and adheres quite well to the carbon. You can see that from the temperature program's reduction. This is the curve for iron. Now for low temperature, this reduction is complete, so there is no interaction of the iron oxide with the carbon. With nickel on the other hand, you get a rapid reduction, but then you get metallation of your carbon by means of the nickel, and iron is not doing that because there is no interface of iron. Well, these are the requirements we want to establish, and now is coming the invention. We want to make a bimetallic copper iron catalyst, and here are all the requirements, and it is an endothermic alloy, so we have to be cautious. And then surprisingly, well, it's not surprisingly at all I feel, but if you are precipitating copper together with the iron cyanide, or the iron peroxide cyanide, you get here already on a molecular scale a mixing of the relevant ions. The relevant atoms are mixed on a molecular scale, and then you can destruct, after adsorption of this complex, you can destruct the material onto the support, and over here is indicated the moment of destruction. You can do that in hydrogen, and you see the reaction products, and these will change in weight, or you can do it in oxygen. In an inert atmosphere, it's very difficult to complex. You can do it in oxygen, and then more or less surprisingly, you don't have too much difficulties, because now you are only exposing the oxide or the mixed oxide, because it works as well with iron oxide as with the iron copper oxide we are making by this procedure, but you can also precipitate the iron cyanide, and you are only releasing the oxide at a high temperature where you have already removed the water. And just from this infrared spectrum, you can see that if you are adding CO to the freshly reduced catalyst, you have much absorption of copper, and you have a small absorption of iron. But just to the fact that the CO is sitting there, and the metal atoms in the alloys, even at room temperature, are not stable, but they are mobile, they can migrate, and as a function of time, you see the iron coming to the surface, and the copper, which is in the catalyst exposed to vacuum, there's copper selectively at the surface, and the copper decreases. So by this means, we have a good procedure for producing these catalysts, and it turns out that if you don't have so much iron 2 oxide present in the boundary layer, you get more active catalyst, you get a completely different infrared absorption pattern too. So the reaction of iron 2 with support, especially in the presence of water, gives rise to troubles, and it's advantageous to remove the water before exposing the iron oxide to interaction, and you can do that by the decomposition of suitable complexes. You can do that by impregnation with citrates or ETA. You can do that especially very well with pre-shaped bodies of the supports. You don't have to shape powdered loaded support, but very suitable is the precipitation of the complex cyanides, gives rise to very good catalyst. Well, I hope I brought my message, and I hope, Mr. Chairman, I'm on time, and I thank you for your attention.
We have time for one question. Yes.
How do you get your cyanide support? What is the condition?
Well, that is interesting. We are doing precipitation, and usually they are kind of negatively charged, the cyanide species, and they are just absorbing onto the alumina. Silica is much more difficult. We have to change the charge of the silica, but alumina is no problem at all. It just is absorbing and it gets on the bottom.